forward and backward
Oh,
on the scale.
okay.
I didn't want to plug it in anywhere here.
Oh, that's okay.
Because it has screwed up things before.
Why does it need to? So it's gonna be.
Forward and backward.
Do we have to? I don't know.
Additional interface need. It's needed to be.
So.
That's just really bad.
Oh, I don't need that. Okay. But is this?
Theoretically, you just plug it in and click. And it should work.
Oh, there we go. Okay, perfect.
And
Okay.
then the green button on this is a laser pointer.
Ah, okay.
If you want that as well.
That sounds good. Let's get this away.
Lapel mic, you actually do need to be fairly close to your mouth. It's on in live.
I made it. Hey, oh, you done? I'm so used to the 10 after thing, so I don't know if
Was that Berkeley time? 10 after?
Yeah, they started recently, which I've been late to the last two talks I went to.
It's harder to traverse campus because every student's affixed to their cell phone. I don't think the undergrads can walk without a phone anymore.
It's ridiculous. Nobody's paying attention to anything but their smartphone.
Would you hear this? There's one school that actually took one of their wide stairways and they painted it up, down, and on your phone, thinking that it would get people's attention. And the people looked up enough to just go into the on your phone thing and kept.
Does the smartphone come with an app that tells you when you
Left, right, left, right.
Not mine.
So I'm going to introduce you.
Okay.
I guess we're good.
All right, let's go away.
Sorry, I just traversed campus in here.
Okay, hold on.
I'm happy to introduce Ann Almgren, visiting us from Lawrence Berkeley National Laboratory. Ann is the group leader now of the Center for Computational, I never know if there's an S at the end.
There is an S.
Sciences and Engineering. I think you guys get that wrong sometimes too.
We do.
Yeah.
We do.
Ann did her undergraduate at Harvard, graduate in mechanical engineering at Berkeley,
Yep.
and went to Livermore
Yep.
straight after that. And then the group as a whole transitioned to Lawrence Berkeley Laboratory, where she's been, well, we won't say for how long.
Since 96.
96. Okay. I started working with Ann in 2004, I think, gradually pulling her into astrophysics.
Yeah.
And Ann's been teaching me all about low-speed flows and projection methods, and we're happy to have her helping us out with the astrophysical hydrodynamics. Ann's an expert on adaptive mesh refinement. She's going to tell us about some of the ideas for the next generation of adaptive mesh refinement, I guess with an eye towards exascale and such.
The dreaded E word.
If it ever comes. And all right, so let's give Ann our attention.
Okay. So do you guys interrupt or not interrupt during? I'm happy either way. Okay, so please feel free. So two comments. So I have an undergrad degree in physics. I have a graduate degree in mechanical engineering, and I have pretended at times to be a mathematician. So the joke is if you ask me what I do, I'll tell the physicists I'm a mathematician, engineers I'm a physicist, so nobody can pin me down. So I'm glad I'm talking to the institute, not your department, because all the astrophysics I know I learned from Mike Zingali. And the fact that I don't know a lot is not any reflection on him. So star charts. You're good. I haven't. So a lot of what I'm going to say is framed in the context that what has been happening in the national labs is we have research budgets in math and computer science that are run by Department of Energy, and they have decided to take a lot of those research budgets and put them into something they call the Exascale computing project. And so if you go to environments where there are a lot of national lab people, you will hear the word exascale thrown around a lot. And sometimes it's with a capital E, which is the Exascale computing project, and sometimes it's a small e, which just means next generation. So I deliberately use next generation here because this is a mix of lower and uppercase E, but it is very much with an eye towards that project. So looking just at LBL, and I'm going to define adaptive mesh refinement in a minute, but I want to just give a sense. Where is it useful? Anytime you want to do a structured grid approach to modeling something, then you might want to use block structured AMR. And the phrase AMR can mean a lot of different things. Some people use it for unstructured grids. Some people use it for sort of tree-based AMR. Some people use it for cell-by-cell refinement. I'm going to talk about a very specific kind, which we call block structured. But just at Berkeley alone, we have. Oh, am I not? Oh, yeah, sorry, it's not even full.
That's all right.
I thought I was, and I wasn't even paying attention. And somebody's calling? Is that?
Yes, that is
Okay. Oh, I forgot. Okay. So at Berkeley alone, we have AMR code. So our group develops algorithms. We develop codes. We run the codes on supercomputers. We write papers with smart collaborators about the science that we learn from them. I would say our group focuses more on the algorithm side, and as a result of this emphasis on Exascale, we do focus a lot on the implementation, how we're going to run them fast to do the next big problem. So we have applications in combustion, and that would be both compressible and low Mach number combustion. In astrophysics, again, there's compressible and there's low Mach number. Again, all those questions will go to Mike. Cosmology is something that it turns out if you take a compressible astrophysics code and you add the expansion of the universe and you add some dark matter, you get cosmology. So we play in that as well. Accelerators is a new project. Actually, 5 of the 6 of these are actually blessed projects. They are Exascale computing project funded application projects. So there's something that for the next 4 years, we get a whole lot of money to make them run on the next generation machines. Accelerators, the current code does not currently have AMR, but it's going to, is one of the paths forward. Subsurface, and then climate is not actually an ECP project with AMR, but it's happening at LBL. So that's LBL alone. We've got 6 of these, and these are major projects that use a lot of time at the supercomputer facilities. At large, we don't own AMR. People have been doing AMR for a long time. It turns out when I originally agreed to give this talk, I was going to give it back in February, and I was going to use it as a dry run for a talk I was giving at SIAM Parallel Processing in Paris in April, and it turned out that I ended up deferring this one. So this is the talk I gave. Anyway, I gave it over in Paris, and it turns out that somebody leaned over and whispered to me that I'd really pissed off the Europeans because to them, AMR meant this cell-by-cell refinement, and I was using it to mean block structure, and those block structure people are taking over the world. Not really true. But anyway, so if you look, so Donna Calhoun has a nice listing of these. The point I'm trying to make is there are multiple AMR frameworks out there. There are multiple AMR applications. It's something that's out there. It's a technique, probably not as common as FFTs and such, but it is a technique a lot of people are using. There are a lot of software packages. For most of this talk, I'm going to zoom in on what we do. But that's not to say that other people aren't doing similar types of things. Okay, the other comment is if you want to run a block structured AMR code, at this point, you do not want to start from scratch. There was a time when, would you have every graduate student write their own? No. There was a time when it made sense to write your own. You can still write your own if you want to run it on your workstation. If you want to run one efficiently on many core machines, it's just too big a project to start from scratch. And so I think that's something we're seeing more and more in a lot of the big applications is it's just too daunting to start from scratch. It's much better to take something that exists and tweak it to your needs. This is a list of people who've contributed just to BoxLib alone. BoxLib is our AMR framework. It's probably, I'm even leaving some people out here. So again, credit to many for the things I'm going to talk about. Mistakes are mine. And in fact, I'm going to talk about some work that I'm not directly involved in, but fits into the bigger picture of this. The power of 10 is something that one of the users did with Castro, where he wants that star there. It's going to get much bigger. It's going to blow up. So he puts it in the domain. Those are a factor of 10 zoom in. So that's the kind of thing you can do with AMR. Anyway, okay. So when I say AMR here, I'm specifically talking about block structured AMR. And we're going to put it in the context, the type of problem I want to solve is time-dependent PDEs. These can be systems of PDEs. They can have constraints. They can have algebraic constraints or other types of things. But that's sort of the general class of problems. And in the world out large, that may not be a huge part. But in the world of science applications, that describes a lot of them. So when we say block-structured AMR, the solution in the end is going to be defined on block grids. Structured, it's structured grids. B, the refinement happens in blocks. And a block might be 32 cubed. It might be 32 by 64, something like that. But I'm not refining a cell at a time. So the solution in the end is defined on a hierarchy of levels. We basically think of the solution as living on the finest level at which there is grid. There is a representation of it under for the purposes of efficiency. But we have a solution that in the red grids there is very finely resolved, and the blue is slightly less so, and the black is what we call the base grid. That's my resolution that's going to cover the whole domain. At every level, I have a union of rectangles. And in our world, those are completely disjoint. There's no overlapping. There are people who do overlapping meshes, slightly different issues. Don't have to have fixed size patches. which is true of BoxLib, not true of some other frameworks. And a key thing for the purpose of running them efficiently is they change dynamically. So we may regrid every 2 time steps because something is moving across the domain. A flame it's moving, it's lighting, all sorts of things happen. This has to be a dynamic process. I think, Max, is this one yours? I think it's the white dwarf. Where's Max? Yeah, this one's yours. Okay, so that's 2 white dwarves. Again, the pink is the finest, the light blue, which you can hardly see, is the next, and then the dark blue. The data that we work with, it's mesh data, so that can be on cell centers, it can be on nodes, it can be on edges or faces, and then we also have particles. Turns out lots and lots of applications have particles, and doing particle mesh operations, it depends a lot on what your mesh looks like. So doing particle mesh operations on unstructured grids looks different than doing them on block structured grids. Okay, so one of the things that we find is, so AMR has been around, there's an original Berger and Colella paper that talked about doing this hierarchy, and they did it for compressible gas dynamics. In the beginning, AMR meant AMR for compressible gas dynamics. And then we did some work and we did incompressible flow solvers, so we could do incompressible Navier-Stokes solvers. But the thing that we find is that when people hear AMR, there's something that we have to fight in the DOE complex is everyone knows AMR doesn't scale. Well, that's kind of a 30 years old thing, okay? Everyone knows that with AMR, you have to blank. And the perspective that I take on this is AMR tells you what the spatial layout of the solution is. I haven't told you how you've discretized the equations. I haven't told you how you've time-stepped the equations. And I think, to me, that's where the power of this is AMR is a broad category of it's not even a solution approach. When I say AMR, I'm really telling you that I'm going to let you change the grid resolution, and what you do with that is kind of up to you as the algorithm designer, and depending on what equations you have. So by saying block structured AMR, I've defined the spatial layout. I haven't defined spatial or temporal discretizations. The traditional time stepping was for compressible gas dynamics. And it turns out in compressible gas dynamics, if you want to refine the mesh, you also need to refine the time step. And you could say, okay, well, I can keep that ratio the same, and that's what we call traditional subcycling in time. So delta T over delta X is the same for every level. And that's sort of an optimal way to run compressible gas dynamics, because it turns out the other approach, which is, I've actually switched the orders, if you advance all levels, for example, with the finest time step, A, you're doing a lot more work than you need to, and B, your scheme may actually work better with a larger time step. It turns out a lot of the compressible schemes do. So, Crispin, we need a better phrase than, we call the top one no subcycling, but there really ought to be a better phrase for that. So you could run all the things with the same time step. You could run with what I call traditional subcycling, which is what the early Berger-Colella work had, which is delta T over delta X is fine. So what you do is you take a coarse time step, you take multiple, maybe 2 or 4 fine time steps, and you do some kind of synchronization. And then you can imagine recursively going up to finer levels. So those are the 2 traditional approaches, and that's 99% of what you'll see in the literature. Well, once you have the machinery, it's kind of obvious to say, well, do I have to do the same thing between levels? So we coined the phrase optimal subcycling, where it may be to your advantage to subcycle between levels 0 and 1, but not subcycle between levels 1 and 2. And there's 2 reasons you might do that. One is you may actually have the same time step constraint on different levels. For example, in early cosmology, you may be constrained by this expansion factor of the universe, and that's not resolution dependent. So you may not need to adjust the time step. There are also cases where you may not have enough work on levels 1 and 2 independently. So if you do those separately, you're wasting cycles. You've got 1,000 cores and 500 of them are sitting there. So you might want to advance them at the same time. So there are reasons you might want to do this, and if you build an AMR framework, which we do, then you want to leave that as an option. The last one is something that I'm going to allude to, but it turns out, again, once you have this machinery, you've got a multi-level hierarchy that you can do whatever you want with. And there are iterative schemes that basically allow you to take a larger time step by iterating over the time step with increasing accuracy. So you can take sort of a coarse time step with not very fine accuracy, not very high accuracy, and then you iterate, you use that as a feeder into the second iterative step, the third iterative step. You're iterating over a time step to get to a higher order solution through iterating over each time step. Well, if you're doing something at low order accuracy, the obvious thing is, well, do I need fine grid resolution to do that? So maybe I can use my fine grids as early iterates in an iterative scheme. So now I'm kind of breaking this paradigm that I'm not just marching forward in time, I'm using coarse grids in a different way. similar to, it's kind of a multi-grid concept. In fact, people talk about multi-grid in space and time. So once, again, it's kind of once you have the machinery, you can start to play with these algorithms, and you actually open up algorithm space instead of shutting yourself down. A key thing, so this talk in some sense outlines, we actually put forward in this Exascale computing program, we've put forward the idea of an AMR co-design center. And so what this talk represents in some sense is a path forward of what we would do. We don't know if we're funded yet, was hoping to know by now, but this is kind of where we would go. And so my comment is, whatever we do, it's got to support all these options, because I guarantee the minute that we constrain something, there's somebody out there who wants to do something different. And we find this, we publicly release the software and we do things that we think make sense at the time, and then somebody says, well, this is what I want to do with it. And, good point. No reason you can't. Okay. So again, I'm going to talk mostly about BoxLib, just the features so that we are kind of all on the same page. The meshing is dynamic. So typically, at level 0, we will decompose the domain. That typically stays fixed over time, but all of the finer levels, all of the finer boxes change over time. Okay, they're changing size, they're changing location, so we're de-refining and refining different levels of the grid. And unlike, so the flash code is another one out there that people know about, that has a unique parent-child relationship. So in the sense that every fine grid has a unique parent grid. Okay, we do not do that in BoxLib because that constrains the way that you can create the boxes. So we might have a fine grid that overlaps 2 coarse grids. So when you go to interpolate data, you're looking at multiple grids. It makes your communication a lot harder, but once you've done the work to make your communication efficient, you have the flexibility. So we've got operations, things that happen on a single level, things that happen between levels. Again, so the operations themselves, the floating point operations, and then the communication, of course, both at a level and between levels. Mesh operations, particle mesh operations. A key thing to keep in mind, a lot of people make design decisions thinking only about explicit algorithms. And a lot of the conclusions they reach don't hold for implicit algorithms. It's an obvious thing to do, but it's one of those gotchas that you have to keep remembering when you do implicit. And again, no one approach. We don't want to lock ourselves into saying you have to do a second order discretization, you have to do this. I will say that this is designed for finite volume or finite difference, not finite element. So that is a constraint in terms of the discretization. But we don't want to lock in that you have to do a Godunov method as opposed to a something else. Okay, so I call this key issues. Another phrase for this is what keeps me up at night. So if you ask me, what do I think we need to address to design the, quote, next generation AMR? In other words, if we want to be the framework that the Exascale applications use when they run on the next generation machines that we don't even know what they are yet, this is what I think we have to address. Some of this we will address. We are hoping that other parts, so within the project, there are applications, there are co-design centers, and there are software technology projects. So for example, linear solves are a big issue. There's supposed to be a software technology project that's going to hopefully give us performant linear solves. So this is sort of within the framework itself. This is what I think that we own, that we need to deal with. I want to go through these topics, and I want to kind of give you snapshots of what our thinking is, some of the things we're doing. It's not meant to be comprehensive, and it's also not meant to be a final answer. These are the things I think we need to address, and I actually don't think we know the answers for what's going to work best in 4 years. And the projects are only 4 years, depending on the US response to the Chinese computers, the ECP timeline may change. It turns out that DOE wasn't happy that they kind of got scooped. Okay, so on node performance. One of the things that happens when people start thinking about having a lot of nodes is they focus on everything that happens between nodes. Because my gosh, we've been working on one node forever. There's 2 problems with that. So one is the nodes themselves are changing. And 2 is if you can't get on-core performance, then stringing together a bunch of cores isn't going to be great. And I think that we all like to move on to the new cool thing, but we can't forget that per core performance really matters. Now that is very algorithm specific. Okay, so as an AMR framework, we can't make that work because it depends what you're discretizing. The big change I will say in terms of per core performance is we used to count flops. We used to count how many multiplies, and gosh, if we can replace that log or that exponent by something, that helps. And what we're seeing, I'll give you an example on the next slide, is And I used to discount this. The honest truth is I used to think, yeah, memory access. And when I say memory access here, I'm talking about getting the data out of memory in order to operate on it. So I'm not talking about moving it across nodes or anything, not over the interconnect. Just pulling it out, if I want to do C equals A plus B, I've got to get A and B out of memory. And I used to kind of, they say that. I'll show you some examples where it was kind of my wake-up call. In the category of things that people do for this, so there's auto-tuning, which says, I've got 5 different ways of writing this, and I'm going to figure out which one runs the best on this machine, and I'll do that. Vectorization, there are some people in the room who remember when vectorization was the name of the game. If we could just vectorize. Okay, you're nodding. You remember this? Yeah. Yes, it was all. Well, what's really funny, so we invented BoxLib before there was a parallel version, and we said, should we make a parallel version? It's like, nah, no, we're vectorizing. That's all. And then all of a sudden it became all about parallel, and vectorizing was out the door, and now vectorizing's back. So now you have to do parallel and vectorize. So vectorizing is very much an encore thing, and it's big again, okay? Maybe not for all architectures, and who knows in 4 or 8 years. But these are things that you can do encore. So auto-tuning is, you say, okay, which of these 10 things works best on this machine? I'll just choose it at runtime. Vectorization is the way that you write your loops. Again, it's about memory access. Code transformation is just a kind of a buzz phrase. You hear about that I'm going to refactor my code, and maybe I'm going to use somebody else's software that I'm going to put in my badly written Fortran, and it's going to generate me out this really great Fortran. Communication avoiding algorithms, again, are addressing this point that you have to care how many times you're going in and getting the data. And you can actually change the algorithm. You can pre-compute certain things. You can do things slightly different ways where maybe you're even doing more flops, but you're more efficient. This was kind of my wake-up call for the memory access thing. So logical tiling, some people call it tiling, some people call it logical tiling. There are a couple different phrases. Basically says all your arrays are exactly the same. When you allocate your memory, it's exactly the same. But when you operate on it, instead of looping, when you do an IJK loop in Fortran, instead of looping over the whole K and the whole J and the whole I of a 32-cube grid, operate on it. Maybe you're going to operate on a sort of a, we think of them as 2D tiles, but in 3D it might be 128 by 4 by 4. So I'm doing exactly the same number of operations. I'm doing them in a slightly different order, but let's assume my operations aren't order dependent. I'm just going to call the subroutine more times with a smaller work area. Okay, I haven't changed anything about the data layout. And in this example, if you kind of ignore the region thing, so a grid is the larger, unfortunately the black's overwritten by the red. Those are grids. That would be my 32 cubed. I'm going to break them up into the little blue guys, and those are going to be my work areas. So I've got to call my subroutine lots more times. And it turns out if you do your software right, you can actually completely hide the tiling, so it's not as onerous as it seems. You're accessing memory differently, and you can get a factor of 3.5 speed up just from doing this. So this was my wake-up call that you're doing exactly the same number of flops, and you're doing a trivial thing in terms of the way you access the data. Now, what it actually should tell you is, wow, the GNU compiler is really messed up, because if you look at how long it took, so with no tiling, you're almost 30 seconds here, about 15 there. So the GNU compiler, you would say it sucks. The reason we still like the GNU compiler is after you spent the last 10 times you thought something in your code was broken, you found out it was the compiler bug, you finally say, okay, well, I'm doing code development. I'm just not going to care. I'm just doing GNU. But you can see, so the GNU speeds up by a factor of 3.5 just from the way you're accessing the data. So this to me says you got to care. And I hate this because I'd rather just write my loop. I'm doing what I want to do. This is where the code transformation stuff comes in, right? Maybe I write my loop the way I want to do, and somebody else figures out the tile size. We have decided that software doesn't exist yet, so we own the tiling. So we get to set the tile size. And we might do an auto-tuning thing where we say, okay, for this machine, I got to figure out what the best tile size is. And it may not be the best tile size for all the operations because one of them is accessing a whole lot more data than another one. That might need a smaller tire, bigger tire. Okay, so that was sort of the point of the, and this is, again, just so you know, on the bottom, I've listed the names. This is work that was done by Wei Chen, who's in CCSE, along with, Didem's actually a professor at a Turkish university, and Tan is a former student of hers who's a postdoc at LBL. So a lot of the work I'm presenting here is with collaborators. It's not stuff that I have personally done. Okay, so that's on a single tile, a single core, and then you ask, okay, now on a node, I have multiple cores. And I'm using cores, this is basically a multi-core talk. I'm not talking about GPUs. I personally have less experience with GPUs. We're going to deal with GPUs. I wish GPUs went away, but I can't have that. So we're going to we're going to wait out a little bit some of the language issues they have now and hope that by the time we decide to deal with GPUs, they're a little bit more, the interface is a little bit more standard in some sense. Okay, so now the question is, now I've got, let's see, Cori has 68 cores per node. Well, I don't necessarily want to put 68 grids on a node. And so how am I going to break up the work? And one of the nice things about tiles, again, that I just told you I'm breaking up the work. So now if I'm using threading, so like let's talk about OpenMP threading, I have smaller work units and I can distribute those more evenly. And so that's what we're seeing here. And again, I'm just showing these to point out. So this is a node tiling. You saturate very quickly because you don't have enough grids to go around. And if you have tiling, this is the problem. So this is one node of Edison, which had 12 cores. And so I'm just asking, can I make use of the 12 threads? So I have one MPI process here. It's actually just one node. But I'm using 12 threads using OpenMP. Here I saturate around 2. Here I'm up over 12. Okay, so it's a win. I'm just dividing the work into smaller units. This is a similar thing. This is a node of Babbage that has 60 cores. Each core has 4 threads. I saturate here at about somewhere around 120. So I'm not getting full use, but I'm doing a lot better. Okay, so this is kind of the on-node deal. We have to deal with this. This is not AMR specific, but when we do AMR, if we leave this out, we lose. Okay, so that was topic 1.
So I would look
Yeah.
at that, and I'm looking at the left graph,
Okay.
and I would say that, okay, if you go down to just a single node.
Okay, so this is one node.
Never mind.
Yeah, yeah.
My question was there.
Okay. Yeah, the other one was one core. This is one node, so I'm not doing MPI between nodes. I'm just doing threading over a node. So this is basically about what's happening with the nodes. I mean, it's this litany that you hear. The nodes are becoming, so you're going to have more cores or more processing units. It might be core. So let's call more processing units per node. The processing units are going to have more heterogeneity. So that could be cores. So they talk about lightweight cores versus not lightweight cores. You have GPUs plus CPUs. You have more heterogeneity of this capability. You also have much more complexity of memory. So you have more heterogeneous memory, and so you have to worry about where are you putting your data. And we are now worrying about things like, okay, so I know I'm going to access this array 5 times. I'm only accessing this one. So can I tell the machine to store this array in the memory that's quicker to access? And then you got to ask, okay, but now if I'm 1 byte over, it kicks out and it gets, yeah, did you want to comment on that? Or?
Well, I mean, given one thread, if you go to tiling, you see, I mean, I'm just looking at one thread on that.
Yes.
And you see significant speed up when you go to tiling versus no tiling.
Right.
I mean, that would tell me that you're you've got memory access issues.
Oh, no, that's exactly this, right? So even on just one core, one thread, there's no threading or anything here. This is just one core doing a 128 cubed array. And I'm just accessing into it and doing some relatively simple operation.
Right.
Just the order in which I access it is making a factor of 3 difference in my performance. Yeah.
We're in agreement.
Okay, so that's what this is right here. That difference.
Yeah.
Okay. So we're saying the same thing?
Yeah, we're saying the same
Okay.
thing.
Yeah, so you get that from what we talked about in the previous slide, and then the fact that this doesn't go anywhere is the fact that I don't have enough work to spread out.
Right.
And it's a stupid thing to do. I mean, this is a very naive thing. Why would I use 12 threads if I have 2 or 4 grids? But the point is, there are reasons for breaking grids up the way and the grids, when I say a grid or a box, that's what I showed you there. So there are 2 red grids. There are, I think in this case, 2 blue grids and 1 black grid. Okay, so those are the units, and when I was at the talk in Paris, and somebody said, well, doesn't the metadata kill you? And it's just, no, the metadata doesn't kill you. Because boxes are really identified by index space. Okay, so I have to know what level, and I have to know the lower left corner, and I have to know the size. As a finite number of integers, what we can't do is cover the whole domain with 4 cubed boxes. So there's a reason we don't go down there. If we're looking at 32 cubed, 64 cubed, on the problems that we're going to be able to do, we're fine with metadata. But what that tells us, so I say we're fine with metadata, we're fine, but that kind of constrains us. We don't want to go down to tiny grids. The other reason is the surface volume effect. So grids tend to have ghost cells, so that when I'm doing an operation, I'm not reaching over to another grid at that moment. Well, if I have a 4 cubed grid, I've got 3 ghost cells. I've just effectively doubled the width of my cube there, so now I'm taking a huge amount more memory. So both for the memory and for the metadata, I want to let my grids themselves be reasonably large, somewhere in that 32 to 128 size, but that is not the best way to access the data. And so that's where the whole on-core and on-node game is. And then the other thing, which I'm not really talking about here, is the point of regions here is that I may, on a single node, have multiple Numa domains. So Numa stands for non-uniform memory access. On some of these machines, they're talking about, it turns out with the chips that they just got for Cori, they can basically have 1, 2, or 4 Numa domains depending on how they boot it, basically. And they're trying to figure out if you know you have localized memory and you can use it effectively, you're better off than making the memory flat. But if you can't use it, you're going to kill yourself. So it's kind of a trade-off, and I don't know. This is what Brian was playing with.
In your submission script?
They were sort of talking about that. I'm not quite sure. It's a question of what do the people who run this computer, what do they get to control, and what do you as a user get to set at runtime? And they might have some nodes where you get to, or they're talking about, do they allocate part of the machine to be this way, or do they let you control it? And there's trade-offs for all of these. Okay, so that was kind of on node. I kind of hesitate to put up this slide because I am not an MPI or an OpenMP or a UPC++ expert, but there was sort of this move in this Exascale program to say, okay, MPI plus X is the answer. And it may be. I'm not saying it isn't. X, in most people's minds, is OpenMP. And again, I'm talking not GPUs for now. I'm going to leave the GPUs aside. So the current paradigm in BoxLib, we would typically have maybe a process per, we have 1 to several grids per MPI process. We would break those up into a bunch of tiles, and we would use OpenMP to thread over those. So that was our model on Hopper, Edison, and Cori phase 1. So flat MPI would be great. Okay, flat MPI is easy. You don't have to deal with the threading model. The problem with flat MPI is you would have to have too many grids, which kills your metadata. Your grids would be too small. That's the go cell thing. And it turns out that MPI, we found when you get over like 20, 30,000 MPI processes, you start to take a hit. So flat MPI isn't the answer. So some kind of hierarchical programming model is the answer. What we've done in BoxLib is we have multiple implementations. So you can run flat MPI, you could run flat OpenMP, you could run MPI plus OpenMP. And then there's this UPC++ is something that's developed at Berkeley. So it's nice when you have the developers. It used to be down the hall. Now they're in a different building. It is I'm not sure if they call it a library. It's a parallel programming extension. PGAS is partitioned global address space. UPC++ is a C++ sort of wrapper for PGAS. What it enables you to do, instead of explicitly doing MPI send and MPI receives, you actually, in a sense, have access to, from your perspective, you have access to all the data. There's a global address space, and you say, I want that piece of data over there. You don't have to say, oh, I know you live there. Let me ask you for it and get it back. So it makes a lot of sense because, in some sense, you're removing this whole handshake. Right now, we've done preliminary experiments, and it shows some benefits. And so what I would just say is I think that we can't assume that MPI plus OpenMP is going to be the answer in 10 years. I don't think we know what. These are just some very limited tests. If you look, it's time, so lower is good, lower is less time. And if you look across these axes, this is flat MPI, MPI plus OpenMP, MPI plus MPI. When I say plus, the plus is at the node level. So there's how are nodes talking to each other, and there's how are things on this cores on the same node talking to each other. So, and then here's UPC++ by itself. It's basically all the combinations. And if you look at this test, UPC++ is a winner, and it's about a factor of 2 faster for this. This is a communication exercise. Okay, it doesn't affect computation. This is all about communication. So what I would just say, and this is just a different test, but again, hierarchical UPC++ is a factor of 25% faster than uniform. So I put this up here just because this one sometimes surprises people. I don't know where we're going with this. I'm not sure what the answer is going to be. Yeah.
I'm confused. Why
Okay.
is MPI plus OMP slower than MPI?
Because of the thread overhead. Because if you're doing a small number of processes, like flat MPI is often a win. Well, in this case, OpenMP is actually slightly a win. In this one, it's a slight win. Here, it's not. So you have the overhead of starting up threads. And in some jobs, it's a balance. In some jobs, the MPI overhead is worse. In some jobs, the OpenMP overhead is worse. There's a sweet spot. Yeah. So for a lot of things, up to like 20,000 cores, if you can work the grid size, flat MPI is actually better. So you have one MPI process per core. MPI does all the interbox communication. There's a trade-off there. Yeah, and it's basically because these things have overheads, and how that overhead is amortized, how much work you're amortizing it over. So this, again, it's very preliminary. It's not meant to be a conclusion, but it just says, we got to keep this open. We don't quite know where we're going with this.
Do you see at all Fortran with co-arrays being any kind of a player in this at all?
So yes. And we actually do, so comment one is we do use Fortran for our higher level stuff. And it's been explained to me that Fortran is going to continue to be the win because when you're doing multi-dimensional arrays, the assumptions that are made in Fortran allow it to go fast where the assumptions in C++ don't. So that's going to basically stay for the loop level work. For the sort of the memory, the data layout side of things, like if you're doing all Fortran, I think, so what I'm seeing, and I'd be interested if this is what you guys see, is the computer scientists work in C++. So in some sense, the next advance typically happens in C++. And then Fortran plays catch up, right? So it used to be you couldn't do dynamic memory allocation in Fortran. Well, you could do it, so we used to allocate it in C and send it all to Fortran, and then Fortran, you can pretend you're doing dynamic. So do I think there's anything inherently about the language? No. But I think that the advances are always going to happen first in C++, and then Fortran will catch up to it. So I actually love Fortran. We're actually making a design decision that we're going to keep our core level stuff in C++ because we're trying to be able to take advantage of whatever they do, sort of the cutting edge computer science stuff. Yeah.
No, I was more curious about whether you saw co-arrays as basically being a viable way of parallelization across this situation and replacing MPI plus X.
So I don't know enough about co-arrays to really say anything. Okay. Yeah. I would just say in the past, what has been our experience, that Fortran's usually playing catch up to the fastest C++, for better or worse. And those are basically C++ and Fortran are the languages that we're talking about. Python is great for wrapping. Although somebody was telling me recently, on one of our projects, they have a huge problem with Python because of the way they load modules, and this kills large-scale Python things, which was news to you. You heard this? It was news to me. Okay. So load balancing. So it turns out that there's this mantra of AMR doesn't scale. And if you think about traditional AMR where you're not trying to make it scale, then yeah, it probably won't scale. And when we talk about load balancing, there's two pieces of that. One is how much computational work am I asking each core or node to do? And the other is what's my communication pattern look like? In some sense, the first one's the easiest because I can do work estimates and say how much, some of them are going to be the same every time step. If I do the God box, I'm going to go through the same if tests, same amount of work. Things like chemistry change a lot. If something's burning, it's doing a lot of chemistry or doing a lot of reaction rate calculations. If I'm in a quiescent zone, nothing's happening. And one cell may be burning one time step and not burning the next, or actually more vice versa. But in some sense, that's a little bit more tractable. We can measure the work estimates. We can maybe predict the work estimates. If communication were free, we can allocate the work, and maybe again we have to break it into smaller chunks so that we can get more even balance. That's traditionally what people think of as load balancing. We're now including the communication costs. And now it's an optimization problem, but it just got a whole lot harder. And one of the things I have to think about is not only what is the optimal layout of data, but how much does it cost me to get there from where I am? And this is not something, again, we have the answer to. We're taking sort of a two-pronged approach where the first one is, I'm going to call it predictive load balancing, which is say, let me figure out before I start the calculation how I should lay things out. And this will, for example, tell me the optimal distribution of grids to processes. I might find things like the optimal tile size for operating on these. If I do it in a predictive way, we have a model for it. So one of the other things I want to do is, so again, if I know what the optimal configuration is, I may not be there because I have a different set of grids than I had the last time set. So I have to factor in how much does it cost me to get there. And that's true even if I forget the communication cost during the time step. I still have to move data to get into this configuration. Is that worth it? One of the nice things about having, if you make a model of this that you can run without actually running the simulation itself, is you can assess two things. One is you can assess current and future architectures. So if they say, okay, we're going to give you, this interconnect, this topology, you can ask, how is my application going to do on that? And the other thing that you can do is, here's your machine. It has this topology. What are you going to do? There are times where you have algorithmic choices. And this is just an example. So in the world of solving problems with multigrid, there are two sort of popular types of cycles, and one is V cycles and one is F cycles. And it turns out V cycles kind of hit every, and these are multigrid levels, so they're from the AMR levels down, where down is coarser. The V cycles, as you can see, they kind of hit every level evenly. F cycles spend more time at the coarse levels. And you might say, well, gosh, one F cycle, so that would be one F cycle, and this is 3 V cycles. F cycles are a lot more expensive, but you converge with a lot fewer F cycles. Is it faster? It depends on your architecture. But you can answer questions like this if you have a good model of your system. So that's sort of a plug for being able to model it. What that looks like is this. Okay, and this is something that Sai Chan and his collaborators have been working on. So you start with, for example, a Castro, which you've heard a couple people in this room have used. And you use that, you have a real simulation, use that to get a set of boxes, okay, that you might have. You put that into a box list format and you put it into this thing called Programmer. And Programmer takes information about the box list and about the algorithm, how much computation. It doesn't actually do the computation, but it says, how many floating point operations do I have? How much memory access do I need? And what kind of communication do I need? It creates the XML here. I put that into a simulator, and I get some estimate of performance. And so now I can start to play with this because I can say, okay, let me, instead of 64 cube boxes, let me run with 32 cube boxes. Let me change the way I do an algorithm. Let me use a higher order algorithm that maybe needs more ghost cells. I can try and answer all those questions ahead of time without actually running the simulation. Because as anyone who does timings now knows, the machine variability will drive you nuts. So you want to compare two algorithms and you run them and, oh, this one's 50% faster. Well, that's because it was Tuesday. And on Wednesday, it's 50% slower. And it absolutely drives you nuts. Yes? You're not smiling? No? Yeah. I finally got to the point where I don't want to test anything anymore. Just run it. Just run it. So this at least, it takes away a little bit of the headache. You probably keep some more of your hair. You obviously have to calibrate this. So you have to calibrate this to the machine, and then you have to, then you have a data problem, right? You have all this computer science data. So this is really good. Again, it allows you to assess architectures you haven't seen yet, and it allows you to make algorithm choices, which hopefully, if you average over a large enough time, maybe that will tell you something. One of the things that you learn is, I just told you, wow, let's put all this thought into where we lay out boxes, and I'm going to put box 1 next to box 2 put box 1 in my world on node 1 on the machine, and box 2 in my world on node 2 of the machine. And one of the things you realize is, first of all, in the way we were doing this, we were doing all these algorithms based on box 1, node 1, box 2, node 2. Well, it turns out that when you go to run a job, you don't know where your nodes are. There's no reason that node 23 is next to node 24. So all this time we've actually been kidding ourselves, right? That's actually not true. On a node, there is a certain locality, but you can have nodes completely across the machine, and you think because they're 23 and 24, they're next to each other. And what this shows is, so this was we did some box mapping, and this is completely random box distribution. This is round robin. This is space filling curve, proximity filling curve. I can't remember what the other ones are. We tried all these things, and if you look at this, so again, this is time, so low is good. If you look at, so you want to kind of look at the baseline. No compute says it's all computation time. But if you look at it, random's not bad. So this kind of told us, okay, we made a really nice theoretical construct. It was kind of irrelevant. This is just a slightly different one. Again, these are different distributions. Here's random. It's not the worst. Some of them are worse, which is a little disconcerting. Random's not so bad. Okay, this actually isn't the right answer. What this tells us is we haven't used the information about the topology right. And so that's kind of a next step is to say, okay, now are these nodes really next to each other? And it turns out you can now get that information off the machines. The thing you can't get is unless you're running on the whole machine, you don't know who else is sending data across the interconnect that you're assuming is yours. So this is a hard problem, and there's going to be some amount of compromise of kind of living with what you have. So then it turns out you say, okay, so all this theoretical stuff, it was great. It's a really hard problem. Okay, so let's go to brute force. And so we have real-time profiling. We've kind of done our own profiling stuff because we know what we're looking for. And this is the kind of data. So the outputs is in a database that you can visualize, and there's all kinds of ways of looking at it. And what you can see, so in it, this is node. So X and Y here are node numbers. Okay, and so this is numbers. Actually, I guess blue. Okay, wait, is this in the opposite of direction? Okay, so basically, the upshot of this, I'm not sure what it's measuring, is this is a space filling curve. This is a proximity filling curve. They're just different strategies for laying out boxes. And what you see here is, here are a lot of random nodes talking to each other. And if you look here, it's just much more diagonally aligned. Okay, so nodes tend to be talking to nodes that are near them, right? And in this case, yes, this is just number of sends. This hasn't actually told me anything about the timing, but it does sort of tell me, okay, if I look at this algorithm versus this algorithm, this one is accomplishing what it's supposed to accomplish. Now, of course, what you need to do is map that onto time spent. One of the things that we have done with this, and it's sort of a path forward, is to say, okay, we can accumulate, instead of just accumulating this, a lot of times you profile a code, you step back after it's run, you say, okay, where did I spend my time? Oh, I spent it all in that subroutine. I'll go fix that subroutine, let me run it again. Okay, let's say you've done that to the best of your ability, and now you're running the code, and it's a problem you haven't solved before. So you actually don't know, where the galaxies are forming or where the flame's going to ignite. You don't know how to necessarily do things ahead of time. So what we've set up we have these sidecar core things where you can run, you ask for 1024 cores, you say 1,000 of them are going to be used for the simulation. I'm going to have 24 sitting over here, and they're going to be number crunching. They're going to look at that data. I'm going to get the performance data, and I'm going to crunch it, and I'm going to use it to tell me what I should be doing next. It's a really hard optimization problem. And we've implemented this. We're sort of right in the process of saying, okay, I've got the data. What do I do with it? So this decision-making is really essential. And I told you that you have to worry about the cost of sending that data. We did a test. One of the things that used to happen in this business, I used to trust my gut on this. I say, yeah, I'm pretty sure that'll take longer than that. I give up. I stopped. So we kept saying, yeah, but we have to worry about how much it's going to cost to send the data. If I'm going to move all my data around, I better worry about that. We did a test on one of our complex applications, and basically 1% of the cost of a time step, if you want to completely juggle the data, just send it all over the network to different nodes, it was like 1% of the cost of the next time step, which says, wow, if you can rebalance it, just do it. So the point of this is basically it's a really hard problem. We're trying to develop the heuristics. Some of them are going to be good. Some of them maybe not so much. We need to measure. I think that's going to be the name of the game for the next couple of years, is do reality checks on these machines. Because a lot of our intuition is just not right. Oh, yeah. This one?
Okay, space filling curve. I think I know what you're talking about.
Okay.
You're talking about Pinot Hilbert or Morton or something like
that.
Yeah,
the Morton space filling curve.
What is proximity filling?
So I can't tell you exactly. So you know what space filling does, right? Proximity works harder to put things next to each other. So space filling will get this one next to this one, but now if you go up in Z, you're not necessarily close to that. I can't tell you what the algorithm is, but it's one that prioritizes proximity in the way it lays out this.
Presumably the proximity filling curve knows about the network topology, and the space filling just knows about the MPI rank number.
No, this is this is a little bit of cheat. This actually is just MPI. I'm just looking at MPI ranks.
Okay.
It's actually what happens is if you lay things out in 2D, but then you jump to 3D, you may not have these four might be close to each other, but they're not. Right, and proximity picks that up in some way, and I don't know the actual algorithm.
There's literature out there about this?
Yeah. Or Mike can give you the snippet of code. Yeah, we have all, the honest truth is I can't even tell you what all the acronyms are anymore. GR is greedy, yeah.
Yes, is knapsack, which I think is the default, and that's the worst.
Yeah, interesting, right? So knapsack is very much about.
I'm going to tell Max to go back and randomize all his bugs.
This was a little disconcerting. We weren't happy. Of course, we sent it back to science, like, Sci, can you double check this? Because, that can't be the answer. which unfortunately we do more and more, which is, again, our intuition is not what it used to be, and it's really frustrating. And especially, you know, I say, oh yeah, I'm going to optimize this little loop over here, and I do something and it's slower, and I just, no, I thought I knew. Job security? Okay, so yeah, this is just about node to node. This actually doesn't say anything about time, which would be the real interconnect. It just says how many sends are going between nodes. Okay, so the real-time stuff is a direction we're going more and more. Can we, instead of just profiling it and using that information, which is something we absolutely have to do, can we use it to control the data layout in real time? Hopefully the answer is yes. We've got a bunch of applications we're going to be trying it on. Okay. Now we get into things where I start to, sort of, in some sense, wave my hands more and more. So synchronicity. You hear a lot about asynchronous. Oh, asynchronous computing. You've got to have the runtime do asynchronous. Yeah, we all know that. Okay, we need asynchronous. What does that mean? I guess my statement is it means different things to different people. And so I will claim that there's sort of three categories of it. They are all worth investigating, and some of them are more important or more doable in different applications. So at the low level, you can imagine that, for example, you have a bunch of grids, and each grid has a bunch of tiles, and you're going to do something where you need to get information from another grid, so that's a communication, and then you're going to operate on the data on the grid. And the way we do things now is we say, okay, go and everybody fill your ghost cells, so everybody do this communication at once. Stop. Now everybody go operate on your data. And if you sit back for a sec, you'll say, well, wait a minute. You know, the interior tiles, they didn't need data from other grids, so why couldn't they start computing while everybody else is waiting for communication? And that's just one example. There are a lot of places where at a low level, you can basically, they call it overlapping. You can overlap communication and computation. And so you're doing things, in some sense, all of the cores are not doing the same thing at the same time. You are operating asynchronously. Also, communication hiding. This is something that can be automated. Basically, a runtime system can do this. There are different degrees of runtime systems and how they handle it. But that one, I think, is kind of a no-brainer. You want to use that to the best you can. Not clear how much of a win it is. It is, in some applications, it's a big win. Others, not so much. Now you get to what I'll call medium-level asynchrony, which is just because I couldn't think of anything else to call it, where let's imagine that you need to do multicore. You're going to do a diffusion operation, and you want to do a diffusion operation on 4 different species. Right now, in the code, the only way we have to tell is we say, do the multigrid solve for species 1. When you're done with that, do the multigrid operation for species 2. When you're done with that. You can see there's a lot of waiting there, right? And it turns out that with the multigrid operations on a single species, using the whole machine for that may not be a win. So you might like to do these at the same time. And then if you're really good, you might say, oh, okay, so while I'm doing a really intensive part of one, maybe I'll do a communication intensive part of another. So I'm really going to, I'm doing these things sort of at the same time, but not quite at the same time. That gets a little harder, okay? And that's now at the algorithm level where I've had to change the way I specify the algorithm, and I, as the algorithm designer, have to know that solve number 2 doesn't depend on the results of solve number 1. And then, but it's still sort of within one task, which is diffusion solve 4 species. Then the high-level asynchrony is, wow, I really want to step back, and I'm going to make this graph of dependencies, and I'm going to see, can I do 2 completely different tasks at the same time? And there you've really got to know a lot about the algorithm. The statement I will make is there are a lot of people who get really excited about making the graphs for these things. They tend to be really great for simple problems. When you get into a multi-level, multiscale, multiphysics problem with AMR and different components of the algorithm, this gets to be a mess. So our claim is basically, you know what, the person who wrote the algorithm knows what the dependencies are. Let's try and kind of piecemeal take advantage of that, as opposed to stepping back and say, let's spend the next 5 years building a system to discern those dependencies. A lot of times when you do that with the dependencies, you end up having to use a lot more memory because you can't update in place, because that ruins your dependencies, your graphs. Again, kind of a hard problem. So again, low level, definite win. Medium level, definitely need to do some stuff there. high level, going to be kind of algorithm specific. This is just, this is something right now, if you look at the 24,000 cores, we've got about a 30% speed up with doing things. Again, it's an asynchronous runtime that lets you do this, update some tiles while you're still filling ghost cells somewhere else. So you may be looking at 30% is, I think, probably an upper bound. I don't think you're going to get a lot more than that. But, maybe worth doing. Every 30% adds up. Okay, so now we get into what's, in some sense, even more fun. So if you're not the computer scientist, this is where it starts to get more fun, which is kind of coming back to that upper level, that what I call it, the higher level asynchrony. So can you actually tweak the algorithm itself? And there's one thing we're saying, here's the algorithm. Gosh, I've realized I can overlap two pieces. Maybe I can change the algorithm. Maybe I thought I needed something, but I can actually use the lagged version of that. So you start looking at algorithms recently. So can you modify the algorithm? One of the things that actually I was at a talk about Charm++, which is one of these runtime frameworks, an entire talk about removing synchronization points. So it turns out if you let each core do its whole thing for the whole time and don't ask it to talk to anybody else, you kind of amortize over the places where there may be noise, where something may be slower, something may be faster. If you're synchronizing all the time, then you're always waiting for the slowest guy. So maybe you can change the algorithm so that you don't need the synchronization points. This is kind of coming down to something I referred to before with this multi-level approach I was talking about with the iterative scheme. Instead of thinking of a time step as I'm going to start here, I'm going to march forward. End of story. You think of an iterative approach where I'm going to take one step with a relatively low order scheme. I'm going to use that to feed in and do a better job on the next step. You start to have all kinds of asynchrony you can play with. This is something that Mark Day is working on. He's in our group. And this is a little bit, I have a hard time parsing this graph, but basically on the left is the way we do things. And as you can see, time is that axis. So if you look at a specific moment in time, all the cores, which is, let's see. So this axis is all the cores are doing the same thing on a single field at any, so if I pick a time, all the cores are doing the same thing. That's the way the algorithm's written today. You can, and then once you finish all of these operations, this is diffusion, now you do the chemistry, you do all the operations across all the cores right there. You could think about redesigning this algorithm and you get something like this where a subset of cores are operating on a subset of fields for a subset of the time. And so this is what this would look like. And then at the same time as you're doing these diffusion solves, you're marching forward with the chemistry. Here you're using fewer cores, but for a longer time. This is just one example. You start to open yourself saying, wait a minute, okay, so I've gotten the last drop of water or blood out of the stone. Now let me change the stone. I'm not sure I like that metaphor. But anyway, so you have a time stepping. You know that if you converge, you've gotten the answer. So you're still comfortable with the order of your solution. But you've really changed the operations that you are trying to do on the computer, which means you've opened up a new set of possibilities of ways to make it go faster. Another thing, which we're running out of time, is so new equations. And this is what Mike and I work on is there's the compressible formulation of everything. Explicit compressible methods are limited by a time step constraint that sees the sound speed. You make a low Mach number formulation, you don't see the sound speed. You can run with a much bigger time step. There's a trade-off in the time step costs more. One of the things with having a multi-level framework is, so just low Mach versus compressible has nothing to do with AMR, but it's an example of how you might change your equation set to get there more quickly. But the other thing is, you could, for example, think about having different descriptions of physics at different levels. You could have a particle description of the fluid in a fine area embedded within a continuum model. And then something that we're playing with recently is you can have a low Mach number model embedded in a compressible model, where the low Mach number model basically kills the sound speed in the region where it's highest, so you don't have that time step constraint, but you want the acoustic effects. So there's just a whole world. If you're an algorithm designer, things get really fun. This is one that says, you know what, we have to deal with the problem of a whole lot of data. Everyone's kind of moving to in situ in transit, so we are too. That's that statement. And so that we can finish on time. So conclusions, lessons learned. There's a lot of work to do. So for the young people in the room who want jobs, there's a lot of work to do. The U.S. is investing in these machines, and We want to be able to run the big problems on the big machines, and it's not going to be easy. It's not business as usual. And we're all kind of ramping up for this. So comment 2 is we got to collaborate, right? I mean, I know some astrophysics from Mike. I know a little bit of computer science. I'm not an expert in a lot of these things. One of the jobs I do is figure out how to put all these together, to talk to the computer scientists, to talk to the applications, to talk to the, well, actually, I would call myself an algorithm designer. How do I put those pieces together so that we can do this? And the other thing that I hope that you take away is we don't have the answers yet. You know, a lot of people can stand up here and say, this is what I do, and it's great, but there's a lot of moving pieces to this. Just like I said with the MPI plus X, I don't claim to know what we're going to be doing in 10 years. So one of the important things to me is we have to keep our up from where I stand as a developer of BoxLib and the framework is we have to keep our options open so that if somebody does come up with a new algorithm, we're not standing in the way. Thank you. I don't know, you guys finish on time or?
I think we can take questions.
Okay, are there any more questions or? Yeah.
Is there a connection at some level between BoxLib and Chombo? I guess I'm not aware.
So there's a historical connection that Chombo actually came out of BoxLib because Phil wanted to do embedded boundary. Okay, so on the same hallway at Berkeley Lab, there are 2 different code frameworks. There's BoxLib and Chombo. At Livermore, there's Samurai. At Chicago/Argonne, there's Flash. BoxLib and Chombo are probably more similar than a lot of them. They have put a real emphasis onto the embedded boundary functionality. So I would say where we have gone much broader in terms of supporting more different kinds of algorithms, they have focused on the, in some sense, the not the mechanics, but the gory details of making the embedded boundary work. Is that? Sorry.
You're in C++, if I understood that correctly?
So we have the core that we're moving forward with is a C++ framework excuse me, that calls Fortran subroutines. Because we found that when we're looping over multidimensional arrays, Fortran still wins. At some point, we decided to do an experiment and say, what happens if we replace the whole thing with Fortran 90? And so, in fact, the Maestro code that we have is one of those experiments. I shouldn't call it an experiment. It's a great code. It's a legacy code now. But so we actually have an entire framework that's pure Fortran 90. What we found is that it's too hard at this point to maintain both of them. What we've got actually is a new way to, now the languages are catching up, I guess. We can actually write pure Fortran codes that are hiding, they're basically with bindings to the C, so we can use the C++ infrastructure, but write what looks to be a pure Fortran code. We're moving towards that model. Basically, again, it's a sociological one, which is the computer scientists work in C++. And so that's kind of where we have to keep our low-level stuff. That's where the runtimes are coming in. But we thought at a point there might be a win with being single language. I don't think that's going to happen. I think that multiple languages, if you're really trying to get efficiency, I think the C++ Fortran is kind of the sweet spot right now.
And how are you navigating the pace of change in C++? I mean, after a decade of stagnation, now it's got a lot of momentum. Maybe mostly for the better, but it's a huge language. How are you navigating all of this in your project?
So a combination of things. So one is sort of the point so a lot of our thinking now is focusing on this ECP. And within the ECP, there are these software technology projects, and some of them are very much tied to the C++. I mean, they're not about C++ per se, but they're tied to it. So there's a sense in which we are counting on our ties into that community to give us a heads up of what's coming, and then make sure that we're on pace with that. I mean, the problem, of course, is also that, I mean, new features are A, buggy, and B, don't necessarily exist on all your machines at the same time. And we are cutting edge in terms of what we're trying, but we're not necessarily cutting edge in what we can release, because if it won't work on 90% of people's machines, it's not useful. So I would say basically by staying connected with the people who are doing those. Same thing with the hardware. So, we talk to the people who are talking to the vendors to try and have a heads up of what's coming. So we probably get access to information about the hardware before universities do, for example, because we're well connected in that sense. What we can do about it, there's always a lag. But yeah, no, it's a hard problem, and it's a really, the landscape is really complex, and there's a lot of people doing a lot of different work, and I mean, one of the other things that happens, so C++, once it makes it into the language standard, it's there. There's a lot of cutting edge stuff that people are doing, like Charm++. I actually went to 2 talks on it 2 days ago, and by a guy who, he's a graduate student, he just finished up working on it. He's now I think, the CTO. There's a Charm Works or something, they made a company. It has a lot of promise. We'd love to use it. What happens if they aren't there in 5 years? And people can say the same thing about us. So once it's in the language, we're pretty comfortable with it, but there are a lot of cutting edge things that we'd love to use, but we have to be a little careful, and that's kind of part of the complexity of it. Yeah. So, any other questions? Yeah.
Yeah. So the HPC aspect is great, but my question is about the math side of that.
Okay.
Is anybody looking after the stability and conservation issues in these different, subcycling strategies? I would imagine 80% of those combinations would not be stable, and if users just try them out randomly, and they end up wasting time.
So, yes, that's okay. So, yes, that's true. So most of the time, for example, the prototypical user would be somebody who has a single grid code. So they have a method that they're comfortable with, and they might like to run it adaptively. And so the first thing we have to ask is, so one question is, yes, what is the relationship between dt and dx? Because what we're doing is we're letting you change dx in the same calculation. You need to know, does dt scale with dx? Does it scale with dx squared? So whoever came up with that algorithm needs to know that before they can use it, right? But it's the same thing, the same question they would need to know if they're going to run a uniform grid calculation at one resolution and a uniform at another. So in terms of stability, they've already hopefully answered that by running at different resolutions. That time step constraint has to be satisfied in whatever they're going to do. Okay, things like conservation. So for gas dynamics, the synchronization step I talked about. So if you take, for example, you take 1 coarse grid time step and 2 fine grid time steps, and you have fluxes, then if it's purely explicit, like gas dynamics, then there's a known thing. You say, okay, I'm going to replace the coarse fluxes by the fine fluxes. That guarantees conservation. So in the easy cases, we know what to do. If you did a parabolic solve or an elliptic solve as part of your operation, there's a more complex synchronization. There are equations for which I'm sure I probably don't know what the correct synchronization is. So that's definitely on the, the math algorithm developers side of things. If you don't know how to do that right, then AMR is not a magic bullet. So in that sense, I mean, yes, you can do stupid things with it. And that's sort of like we provide ways to refine. So here's the question: what do you refine on, right? And so in the initial work, there was this whole Richardson extrapolation where you said, okay, let me run a coarse time step. Now let me see what would happen if I ran that even coarser. Did I get too much error? If I got too much error, oh, I need this resolution here. So they actually did something where they assessed actual error in the solution. That you can't do that with these multiphysics problems. So the question, where do you refine? Okay, if you're doing incompressible flow, vorticity is kind of the name of the game. So I tell you, okay, I'm going to refine where the vorticity is. That in itself isn't rigorous. When you get to multiphysics problem, well, it actually happens in cosmology too. Where is the mass? So in cosmology, typically they start with the mass sort of relatively evenly but randomly distributed, and you ask, how does it clump? How does it form filaments and things? It turns out that putting an adaptive mesh refinement changes the answer because you're sort of giving preferential treatment to certain regions. You need to know that before you go and use that as a method. And what they actually do a lot of times is they'll run a uniform grid simulation, they'll look at where things happen, they'll go back and put mesh refinement there. Well, then you're still changing the answer, you're just pretending that you didn't. So it's not a tool that you can use blindly. So I would say it's a tool that you can use to do, basically to get to the answer more efficiently. I mean, if we could all run single level, finest time step, finest spatial grid, and just do that, I'd do it in a minute. But we can't, right? It just doesn't fit on the machine. So, yeah. You guys, this is a very popular room.
It's a spam video conference call. I mean, haven't figured out how to kill it yet.
spam your video conference number? Wow. Trying to infiltrate.
We should have a conference where we just watch whatever there's any.
Yeah.
My apologies for that.
Okay. Yeah.
When you say performance, is execution time is your only concern, or are you considering a performance like execution time with some energy constraint or resilience performance constraint?
Yeah. So I was using it loosely to mean time to solution, right? So to me, if I know I want a certain quality of the solution and I can get there faster, I'm calling that increased performance. What I haven't talked about is, for example, the power issues or the resilience issues. And yes, those are there, and I think I'm in denial on those. And there's there's whole fault tolerance. Yeah. The power stuff, I'm kind of waiting for the machine people to come up with better guidelines for us. I mean, there are people working the issues of how do we map. So it turns out that there are algorithms where you say, okay, if I'm not using a core, let me kind of put it into a sleep mode. And is that the kind of thing you were talking about with power? Yeah. So you can absolutely do that, and that makes my head hurt to think about being able to turn cores off and on and do it in such a way that I'm not waiting to wake them up again, and I've really got to know what's going to happen. And right now, I'm with the variability that we see just in raw timings, I don't even know how to factor in that level of complexity. So it's important. It makes my head hurt. Yeah.
They start charging you per watt in the allocations they give you. I think people are going to pay attention.
So the way I say it is I feel like everybody has a line, everybody has a threshold or a line that they just don't want to go below. Like, I don't want to write assembly code. I don't want to design nodes. And the power stuff is below my line, or below the hood of the car, whichever you like. But yeah, there are things that my brain is full thinking about these things. I don't think I have the bandwidth to go there, but somebody has to. Yeah, and that's going to be a problem. Yeah, like I said, there's a lot to do. So your students will have jobs, Mike, even if they don't want to study stars anymore.
Half of them are going to study.
Yeah.
All right, let's thank Andy.
Thank you. Let's see here. Hi, Jim. Good to see you.
Yeah,
Hey.
hi, good to see you.
How are you doing?
I'm doing fine. I'm doing great. We don't have to have a public conversation.
I think it's still recording, so let's see. I just didn't even turn it on.
There must be an off switch.
Maybe it's that one?